Welcome to this AI-generated recap of Inside Azure Innovations, where we explore Microsoft's latest breakthroughs in cloud infrastructure, security, confidential computing, and emerging technologies shaping Azure's future capabilities. This overview captures the session's core advancements, and we highly recommend watching the full presentation for detailed demos and technical insights that truly bring these innovations to life. Inside Azure Innovations covers an extensive range of work, from mature production features to bold experimental research, all designed to enhance Azure's performance, scalability, and security worldwide. While this recap highlights the essentials, the full session includes hands-on demonstrations and deep dives that are indispensable for engineers and cloud enthusiasts alike. The session's innovations are structured around four pillars: infrastructure, cloud native, confidential computing, and future computing. These areas integrate hardware, software, and system-level design, starting with Azure Boost, a hardware accelerator elevating data center performance, then progressing through cloud-native security improvements, cutting-edge confidential computing protections, and experimental future computing approaches, including optical computing. Azure Boost is a specialized hardware accelerator card that transforms how Azure data centers handle storage and network input-output tasks. Traditionally, these functions consume significant CPU resources using host software, but Azure Boost offloads them onto dedicated hardware, freeing CPUs to focus on customer workloads and vastly improving throughput. The second generation refines this architecture and expands deployment across Azure's infrastructure. At the core of Azure Boost Glacier Peak is a hybrid design combining dual 100 gigabit network interfaces, a high-performance Intel Agilex FPGA for accelerating storage and networking, and ARM processors dedicated to control plane operations. This architecture balances extreme throughput with precise orchestration, achieving efficient hardware acceleration of complex cloud workloads while maintaining flexibility and system stability. Azure Boost 2.0 delivers remarkable performance. Remote Azure-managed disks reach throughput close to 14 gigabytes per second with over 800,000 IOPS even when encryption is enabled, while local Azure Boost SSDs push bandwidth up to 36 gigabytes per second and achieve peak IOPS of 6.6 million. The FPGA enables live updates to the data plane without disruption, and dual network links ensure seamless failover. Firmware upgrades complete in milliseconds, isolating ARM cores from the host CPU. Azure Boost 2.0 now runs on over 20% of Azure's fleet, powering new server architectures, HPC clusters, GPU workloads, and network speeds close to 200 gigabits per second. Embedded ARM processors on Azure Boost orchestrate up to 400,000 network connections per second directly on the data plane. A key feature is Remote Direct Memory Access, or RDMA, which allows virtual machines to share memory buffers directly, bypassing the traditional networking stack and significantly reducing latency. This innovation accelerates high-performance computing and AI model training, with a detailed session demo showcasing the performance leap. Conventionally, VM networking involves TCP/IP layers and device drivers that add latency and overhead. RDMA circumvents these by enabling direct memory-to-memory transfers between virtual machines, eliminating software stack involvement. While originally an InfiniBand technology, Azure Boost extends RDMA to cloud platforms, achieving ultra-low latency and high bandwidth within virtualized environments. RDMA integrates tightly with GPU Direct technology, permitting GPUs to transfer data across the network independently of host CPUs and software layers. This capability dramatically reduces latency and speeds synchronization of large AI model parameters during distributed training. The session demo contrasts traditional versus GPU Direct transfers, highlighting significant gains in training speeds. One standout demo, called Guest RDMA, benchmarks an MPI all-reduce workload running across two virtual machines with 4 GPUs. Without RDMA, bandwidth maxes out near 1.4 gigabytes per second with latency around 51 milliseconds. Activating Guest RDMA increases bandwidth 11-fold to over 14 gigabytes per second and sharply lowers latency thanks to direct GPU-to-GPU communication. This dramatic acceleration is crucial for high-scale AI training. Host updates on running virtual machines usually carry downtime risks, but Azure employs several innovations to minimize disruption. CPU microcode updates happen transparently. Live VM migrations smoothly relocate workloads. Hot patching applies fixes without rebooting, and hypervisor hot restarts maintain VM states by concurrently running 2 hypervisor versions during upgrades. Azure enhances uptime further with driver hot swapping, allowing device drivers to be replaced live, and VM-FU, Virtual Machine Preserving Host OS updates, which pauses VM states during host OS updates and resumes flawlessly. These innovations dramatically reduce outages compared to traditional reboot methods, edging Azure closer to near-continuous availability across its data centers. VM-FU operates by maintaining guest virtual machines and Azure Boost components active but paused during updates. The hypervisor suspends virtual processors and briefly halts I/O to maintain consistent VM state, while underlying hardware continues running uninterrupted. This ensures VMs avoid downtime during critical infrastructure patches, securing workload stability and service availability. Combining automatic virtual processor suspension with virtual function keep alive, many VMs managing direct storage and network I/O remain operational throughout host updates. This seamless collaboration between virtualization layers, guest VMs, and Azure Boost hardware sustains workload performance despite brief virtualization pauses. The session's detailed demo showcases this impressive uptime resilience. VMs that aren't actively using virtualization layers, especially those handling storage and networking directly, bypass suspension entirely, dramatically minimizing downtime. This intelligent design simplifies rolling out infrastructure updates across Azure's global data centers. The session demo provides detailed insights on VM state behavior during host maintenance. When VMs do need to pause, they signal suspension, disconnect cleanly from the host, then resume seamlessly post-updates. Yet the majority avoid interruptions altogether thanks to automatic suspend and keep alive mechanisms, pushing Azure toward near-zero disruption. The full session demo compares these behaviors side by side for clear understanding. The VP Auto Suspend and VF Keep Alive demo starkly contrasts 2 VMs during host updates. One suspends traditionally becoming unresponsive and pausing applications, while the other leverages Azure's uptime innovations to remain fully operational with zero downtime. This advancement significantly boosts Azure's infrastructure reliability, and the full demo is highly recommended. AI workloads require vast, scalable storage capable of ultra-high bandwidth to feed trains of multimodal models. GPUs processing petabytes of rapidly accessible images, videos, and data streams generate terabytes of writes through frequent checkpoints, while thousands of inference GPUs demand continuous high throughput. Meeting these extreme requirements necessitates massively scalable storage systems. While Azure Blob Storage traditionally delivers tens of gigabytes per second throughput, massive AI workloads, such as those powering OpenAI, demand drastically higher performance. Microsoft's solution is scaled storage accounts. Aggregations of many physical storage resources spanning multiple data centers. These scaled accounts offer hundreds of petabytes of capacity, terabytes per second bandwidth, and hundreds of thousands of IOPS. The session's demo demonstrates this scale and speed leap vividly. One demo featured a 320-server HPC Slurm cluster mounting a shared scaled storage account using Blob Fuse. The cluster cached data locally and achieved extraordinary sustained write speeds of 15 terabits per second and read speeds of 25 terabits per second, performance unmatched for today's largest AI storage demands. The full session demo reveals the innovative engineering enabling such massive cloud storage capacity. Switching focus to cloud-native security, Microsoft developed a Linux distribution specifically tailored to enhance container security by enforcing mandatory code integrity at runtime. Traditional code signing falls short for containers, so Azure introduced Linux Guard, which blocks execution of unauthorized or unsigned binaries, protecting container supply chains. Without mandatory code integrity, Linux containers and kernels could execute unsigned or untrusted code, creating serious vulnerabilities. While SE Linux protects hosts, containers need specialized safeguards internally. Linux Guard fills this gap by applying runtime enforcement tailored for container workloads, closing a critical security vulnerability. Linux Guard combines dmVerity's layered file system verification with cryptographic policies linked to container image signatures. At runtime, it validates binary integrity and blocks any unsigned or altered code within containers and hosts. This comprehensive approach raises Linux workload security considerably. The session showcases a live demo of Linux Guard protecting production systems. Linux Guard connects container registry signatures, hardened Linux OS features like SC Linux and DM Verity, and mandatory code integrity enforcement at runtime. Secure Boot ensures all host and container workloads launch only trusted software, delivering a robust security posture vital for compliance and protection in Azure's Linux environment. The Linux Guard demo highlighted how unsigned binaries are prevented from running on hosts and inside containers, with detailed logs tracking policy violations. Microsoft contributed Linux Guard to the open source community to advance container security broadly. In multi-tenant clouds, Azure enforces strong isolation boundaries using Hyper-V virtualization, separating virtual machines, isolated containers, and micro-VM sandboxes running WebAssembly workloads. This consistent security perimeter protects tenants' data and workloads from unauthorized access or interference. Microsoft's Hyperlight Micro VMs are ultra-lightweight virtual machines measuring just tens of megabytes. Using standard hypervisor interfaces, they securely sandbox minimal workloads with very low resource consumption. Hyperlight is ideal for serverless functions requiring strong isolation but minimal overhead. A practical example of Hyperlight is Azure Front Door's Edge Compute platform, where user-defined WebAssembly functions run securely inside tiny micro-VM sandboxes at the global network edge. This delivers serverless compute with ultra-low latency and strong isolation. The demo showed a face cropping function written in C running inside a Rust-based Hyperlight Micro VM deployed on Azure Front Door. Despite typical safety concerns with C code, this architecture safely isolates the workload. The micro VM boots in about 1 millisecond and processes images securely at the edge, demonstrating highly efficient and secure serverless image processing at scale. Hyperlight technology is open source under the Cloud Native Computing Foundation, supporting multiple hypervisors including Hyper-V and KVM. This cross-platform support enables developers to build isolated and efficient applications across diverse cloud-native environments. Azure Container Instances pioneered serverless containers with zero infrastructure management. Recently, innovations added container scale sets incorporating N-groups and standby pools. Pre-created containers kept fully running and ready to launch instantly. The session demo explored rapid deployment of large container workloads using these standby pools. A remarkable demo launched 10,000 containers across 3 deployments, each hosting 2,500 containers, using Azure Container Instances standby pools. All containers were fully live, not placeholders, and deployed in under 2 minutes. This scale and speed empowers seamless handling of sudden workload spikes. The Azure Incubations team drives cloud-native innovation through open-source projects like CADA, a Kubernetes event-driven autoscaler now part of CNCF, Project Copa for live container patching, Dapper, a mature distributed app framework, and new tools such as Radius for infrastructure abstraction and Drossi for continuous application state detection. Developing cloud-native applications is challenging due to complex networking, hybrid cloud environments, Helm, Terraform, and tangled scripts. These complexities slow innovation and demand better platform abstractions that unify workflows across diverse deployment targets. Project Radius addresses this challenge by abstracting infrastructure details so developers focus on application logic. It creates a live graph of app components and dependencies, automates secrets and networking provisioning, and supports environment-agnostic bindings across on-premises, hybrid, and cloud platforms. Radius uses declarative recipes binding application services like Redis caches or MongoDB instances to infrastructure resources. These bindings operate uniformly whether the services run as containers locally or as managed Azure offerings such as Azure Cache or Cosmos DB. Critical to this approach, apps deploy without code changes, adjusting only configuration per environment. The full session demo illustrated this with an open-source trading app example. TraderX is an open-source microservices trading application endorsed by the Finos Foundation and used by financial firms. It runs multiple coordinated services handling trades and data streams. Using Radius, TraderX deployed smoothly on both Azure Kubernetes Service and Azure Container Instances, supporting hybrid and migration scenarios. Service logs confirm successful operation. Combined with Dapper, TraderX exemplifies a modern cloud-native application framework. The session demo explored the deployment and lessons learned. Detecting state changes in cloud-native apps is notoriously difficult due to asynchronous events and data streams, often leading to fragile and complex client-side logic. Drossi introduces a model treating application state as continuous standing queries that update automatically with incoming data, simplifying and improving reliability of change detection. Drossi supports declarative queries written in Cypher with upcoming GraphQL support, monitoring multiple data sources and triggering events when entries appear, update, or leave query results. It delivers function triggers via streaming, polling, or feed methods, abstracting event complexity from developers. The session demo presented real-world scenarios highlighting continuous query benefits. A detailed Drossi demo showcased a curbside pickup app tracking order status from Postgres and vehicle location from MySQL. A continuous query detected when orders were ready and vehicles arrived, triggering notifications, also tracking no-shows and timeouts within one query. This drastically simplifies event-driven logic and boosts developer productivity. Drossi is open source on GitHub, and the full demo is strongly recommended. Confidential computing secures data during its most vulnerable phase when being processed by using hardware-based Trusted Execution Environments, or TEEs. These enclaves isolate code and data during runtime, with cryptographic attestation verifying software integrity before unlocking sensitive data. Microsoft has pioneered confidential computing for over 10 years, deeply integrating it into Azure alongside key partners. TEEs create tamper-proof zones encapsulating application code and data, with attestation guaranteeing software trustworthiness before decryption keys are released. This safeguards data from even hosts, hypervisors, and operators during execution, revolutionizing cloud security by protecting the data-in-use phase beyond traditional encryption. Since 2015, Azure's confidential computing portfolio has expanded to include confidential virtual machines, NVIDIA co-engineered GPUs, Azure Databricks, AKS clusters, and virtual desktops, complemented by managed hardware security modules. Confidential computing has become a core pillar of Azure, enabling unprecedented data protection during processing. The full session offers immersive demos revealing these technologies. A highlight is confidential GPUs that isolate and encrypt AI workloads and data, allowing sensitive models to train privately in the cloud. Although briefly covered, this capability opens new possibilities for privacy, preserving AI collaborations at cloud scale, a pivotal step forward for secure AI. Azure now offers NVIDIA H100 confidential GPUs supporting secure single GPU AI workloads like Confidential Whisper. More recently, multi-GPU confidentiality enables secure generative AI training at cloud scale, setting a new standard for private AI processing on Azure. Consider confidential sales data shared in an environment where it remains encrypted except during trusted processing by authorized parties. Azure combines NVIDIA NVLink confidential GPUs and Intel security technologies to form a confidential compute network that shields data from leaks during AI operations in the cloud. Inside confidential NDV5 virtual machines, H100 GPUs paired with Intel TDX enclaves perform trusted execution with attestation verifying integrity. GPUs communicate over protected PCIe and NVLink links, ensuring data confidentiality with high throughput. AI inputs remain encrypted and isolated from hosts and administrators at runtime. This architecture points toward future cloud-scale protected AI workloads. Looking ahead, Microsoft Research explores optical computing, leveraging light to perform analog, massively parallel computations with minimal energy at room temperature. By modulating light intensity, multiplication happens optically, and sums occur as beams converge on sensors. A live demo showcased real-time handwritten digit recognition using this method, hinting at revolutionary AI acceleration technologies. The optical computing demo used an analog system where light modulation and beam combination inferred neural network outputs for handwriting recognition. While still at an early stage with limited model size, this technique promises ultra-fast, energy-efficient AI acceleration. To summarize, Azure's innovations center on 4 pillars: enhancing infrastructure through hardware and networking breakthroughs, empowering scalable, secure cloud-native applications, pioneering confidential computing to safeguard data in active use, and researching futuristic computing like optical accelerators for AI. Together, these advances equip Azure to offer powerful, reliable, and secure cloud services at scale. For complete insights and dynamic demos, be sure to watch the full Inside Azure Innovations session.